Okay, so let me start by thanking the organizers for wonderful program. So it's my fifth and last week here, and I enjoy enormously being in Florence. So I will talk about paper. As you can see, I gave a talk 2 weeks ago. I had only Italian collaborators mainly, and I still have even for different subject Italian collaborators. So I will try to tell you some very interesting story, which is in a way formal, and I will try, because I understand that audience is mixed, so I will try to please both mathematicians and physicists, but if you're annoyed with something, just let me know. I can switch to another mode. So what I will try to do, my talk is roughly to divide it in 2 parts. So I will first start with BV stuff, so I will just give you some basic reminder of BV, but one of the things which will be very important to me, and I will just review roughly, it's BV push forward map. And I will consider 2 examples. So I will consider what we call Donaldson-Witten theory, and then I will also consider Young-Mills theory in 4D. Okay. Then I will switch. Second part of the talk will be devoted to what we call equivariant BV theory. And I will basically again tell you roughly how equivariant BV push forward works. And the main thing is that we will implement this from Donaldson-Witten theory to Young-Mills, at least in abelian case. And the main result would be that we will get non-local Cartan calculus. Again, my talk, I will try to stay away from technical calculations, but I'm happy to discuss them, privately, because otherwise it will be too technical. Good, so let me start from BV basics. And as far as I understand, there will be a lot of BV talks, so I will try to help those people as well. So typically, when you talk about BV, the sort of the simplest model is that you take some vector space plus a dual vector space with reversed parity, and then you can write some symplectic form on this space. Okay, and then in this space you can of course introduce, so the main thing that if you look at the functions on this space, right, with the reverse parity, then these functions, this is what's called BV algebra, will be. So it means that you will have 2 things. So first of all, at first thing you will have a bracket between functions. Okay, which will be just odd Poisson bracket, which come from this symplectic form, so which would be more or less canonical up to some signs about which you have to think all the time. But secondly, what's important, you will have the operator which called typically odd BV Laplacian, which would be up to the sign, and conventions typically will be something like this. So what's important is that this is not a derivation of the algebra, but the failure of these guys to be a derivation exactly defines odd Poisson brackets. So this is what mathematicians call BV algebra. So again, it's an odd Poisson algebra where the bracket generated by some operator, odd Laplacian. Okay, so then typically what we are doing here, so the main thing in this setup about what's interesting for physicists is the following. Then in principle on this space we have integration, right? So we have a sort of canonical Berezinian measure and dagger. And then we can choose a Lagrangian submanifold here. So we have a Lagrangian manifold submanifold, so which is isotropic submanifold of maximal dimensions, so it's half space. And this measure will induce you, so if I call it a measure, then this will induce me up to some choice of orientation, the measure here on the Lagrangian. And then there are two theorems which people use in this thing. So if I basically want to integrate some, function here, then again, typically write with square root of mu, then there are two facts here is important, that if you basically if this guy is annihilated by 0, then the integral, so the integral depends on homology class of L, so you can deform it. And the second statement is that if f is exact, then the integral is 0. Okay? So this is basically considered the best way of formulating gauge invariance. Then, of course, there is a standard story that we can basically covariantize the things, and I'm not going to discuss these things in details, but the whole idea that this can be easily to generalize to basically odd cotangent bundle of some supermanifold. And the main thing is important that you have to think how to define these things. So you covariantize, there are different approaches, but one of them, for example, you can just choose a volume form here, and then it will define this operator, etc. So there are formulas like this typically that if you want to look at the functions here, then up to the sign, this will be a divergence of, with respect to some I measure mu v of the vector field xf, where f with g will be the same as xf on g. Okay, good. And then upon this choice, typically what you are doing, you're just defining again this integral. So here you choose your volume form, and then it's defined these things, and then you integrate the function f. So there is whole discussion here. There are two things. Instead of talking about volume form here, you can just talk about this object, which is half densities, and basically discuss how this naive Laplacian acts on half densities, and this is the main object. So there are two alternative approaches to these things.
In U sub V, it's V stands for volume.
Right.
So V is a volume.
Right. So quite canonical, what you will do, you will just choose a volume form here, which induce you, canonical Berzinian on this guy, and etc. Right. So to me, for example, the best philosophical way to look at BV, it's a BV, you want to combine two things. You want to combine something coming from vector fields, algebra, and then integration, but integration comes from volumes, from differential forms, and you use odd Fourier transform. So that's, to me, the best way of doing things. Okay, and then quite often in these discussions, you write F as a E S. And then if you impose this condition that Laplace of f is equal to 0, then you end up with the question is S plus Laplace of S equal to 0, and this is typically called quantum master question. And in physics, of course, people put h bar, so h bar will appear here, and then if you send h bar to 0, then this term gone. You consider this as a classical master question. Okay, good. So this is a finite dimensional story which is very well developed since the beginning of 90s, I think. Right. Okay, so far so good. What I want to do is now is the following thing that, and again, when I'm covariantizing anything, everything, all the theorems, modulo some technical things will be true. So I have to choose Lagrangian, if my f satisfies this equation, which is we will typically call master equation, then you can deform L. Nothing depends on details of L. It depends on the homology class. If it's exact, then the integral is 0. So let me just review this idea of BV push forward map. Push forward. So it's very simple idea, and actually we attribute this to Lossev since we heard this systematically from him in 2005. So the idea is the following. So imagine I have my manifold. So I have this this manifold like this, which I can call BV. And it happens to be that my manifold splits in two parts. I will have UV times M infrared. So it's just product of two manifolds, okay? And moreover, I will have my Laplacian also to split in two parts, okay? That what you can try to do is the following thing. You can choose in this subspace a Lagrangian, UV, okay? And then you can try to define the following object. So you will, let me see. So for example, I will define this object. Let me put, so I have an integral LUV t. So t is just some parameter, so I can vary this Lagrangian, and then I will integrate my sigma UV. Okay. So I will skip all this business of half density, canonical densities. This is all assumed. Okay, so I'm taking a solution of, I take my solutions of master equation, which satisfy this guy, okay? And then I do a partial integration. So I'm integrating, so UV stands from ultraviolet, this stands from infrared. So from physicists, you do partial integration, okay? So you integrate some degrees of freedom and you don't integrate others. And then you get object here. And there are two questions what this object is interested for. And then actually there are two statements in these things, which is formal. So of course, this sigma infrared is object on this infrared space. And of course, I assume that I'm choosing this Lagrangian, that this calculation is well defined. But first of all, this will satisfy a master equation on this guy. So the proof is nearly trivial. You just hit by infrared Laplacian. It goes under the integral. Under the integral, you can replace by both, by full Laplacian, and then you apply these things, okay? But another statement which is very interesting is the following, that if you start to vary, if you vary LUVT, then the variation of this guy, so the variation of this guy, sigma infrared, will be exact in these things, okay? So cohomologically, this is well-defined thing. So if everything is defined and you have the splitting, you can produce millions of solutions of master equation. Now, let me make a comment about field theory. Sure.
Perhaps link up to my talk, which is why I'm curious. The thing in parentheses there, are you going to, when you said you're suppressing technical aspects, do you ever use the actual formulas for that?
Well, for proving this.
Oh, no, but does it arise then further down the line?
Not really, no. Right now, basically, I'm just trying to convince you this is an interesting object. Then that's it. That's, yeah. But, if you want to see the proof, you know very well how it's done. Yeah. I'm Ezra trying to make your life easy. Okay. Right. So when we go to quantum field theory, Then of course, life becomes much more complicated because we use still these words BV algebra, right? So we use BV algebra, but in a way there is a problem because we don't have any measure on space of fields, right? So there is a problem with objects like this, because we can write them formally, but they're not well defined, so not well defined. And of course, as a consequence is that BV Laplacian is not well defined. Okay. But what's well defined typically, it's well, to the reasonable extent, it's a bracket well defined. So we basically in BV setup, we pretend when we go to infinite dimensional thing that's, you still try to work, etc. But for example, this object requires regularization. Well, I mean, there is no measure on infinite dimensional space unless you go very deeply in functional analysis. I mean, there is no measure, full stop. Right? That's what I'm saying. But to me, well, let me, before going on, make one conceptual way. I think, of course, it's not developed, but presumably the best way to make this precise, it's going to be with push-forward logic. So basically, in my view, the good BV, at least perturbatively quantum field theory, should be defined as a limits of finite things. So for example, there is this beautiful work by Mnev when he goes to some surfaces, does triangulation. So he replaces infinite dimensional theory by sequence of finite dimensional theories. And in his setup, as long as you define this as a well-defined thing, that's a way to define. But again, unfortunately, it's not developed as a general formalism, and you have to go theory by theory. Also, another very beautiful book by Castello proving renormalizability in this framework of Young-Mills. It's the same way he implements renormalization group flow. He does this cutoff in this setup, and then he basically, in a very controllable way, you can do things. So, in my view, I mean, BV push forward, it's actually a way to define this stuff. But again, it's not developed besides concrete examples. Okay, this was all for general stuff, so let me go to something more concrete and another thing, generality, which I want to say to you before I go to examples is there is this construction which goes back to 90s, AKSZ. So Alexandrov, Kontsevich, Schwarz, Balotsky. It's basically a construction of AKZ solution of master equation. So the idea is the following. So the idea is sort of very simple and very good. So you take a d-dimensional manifold, you shift fiber by 1. So it has canonical integration and it has de Rham differential. Then you take here some manifold, supermanifold, which you can also take a graded manifold, okay? And then you require on this manifold the following structure. So you require that you have a symplectic form of degree d minus 1. And this is typically, in all examples, are exact. Secondly, you require that there is a function of degree d. And then actually you require that if you look at the degrees, this is, sy, then this is meaningful equation. So if you calculate the bracket on y with respect to the symplectic structure, this is 0. Okay. So if you take this data in this, then you can consider space of maps. And this gives you a BV manifold with the following object, which you can write down. So the BV action, AKZ action will be, so if I'm thinking that I have here canonical variables dpi, which dqi, then I can write to you this things, superfields p I dqi plus s of y few P. Okay, and this satisfies automatically. So these guys observed it's very powerful construction. They observed that if you take this canonical data, and this is basically from geometry, it's very easy to generate in sort of if your manifolds have not high degree, you can even classify what is going on, and then you generate the things. So this is very, very canonical. Okay. So let's try to apply this logic, and it all sounds very formal and abstract, but let's go to details in particular examples. That's what I want to consider. Okay, so what I want to start from, 4D theory. We call it Donaldson-Witten theory, but maybe it's not a good name, but it's basically related to the fact that if you do appropriate gauge fixing, it's related to the theory which appears in definition of Donaldson-Witten invariants. But it's defined in the following way. So I'm basically looking at this construction, and what I will do, I will take T1 of sigma 4. And then what's important here, I have to define for you a manifold of degree correspondently 3. And then what I will write, I take a Lie algebra plus another Lie algebra, with the same Lie algebra shifted by degree 2. And I assume that it has invariant metric. So it means that if I write my symplectic form, I will write something like dC A, well, A, which d phi B, eta A, B with invariant metric. Okay? So G is a Lie algebra. So G is a Lie algebra with invariant metric. Invariant metric.
Which coordinate is which?
Which is coordinate A, well, okay, good question. So this is C, in degree 1, and this is phi. Thank you. Okay. And then what I do is I just look at space of maps here. And then by abuse of notations, I will call C fed. It's a corresponding superfield which lands up here, and another superfield which lands up there. Okay. Then, of course, you can ask what's about other part of the data. And again, you can very easily write this data, because what it will be the following thing. This is basically if I write, so it will be phi plus 1 over 2, and then I will have phi bracket of C with C. So if you look at the vector field, this is basically will be well-known wild differential on this space. Okay, so this guy you can check satisfy exactly this equation. Okay.
So this is T1, G1.
This is, sorry, this is, what's the question?
T1, G1. So is the Dungeon lift of the W of Chern-Simons?
I will come to Chern-Simons in a moment. I can rewrite this as a Chern-Simons. So right now I'm just following these prescriptions and I'm writing the things, okay? So if I write for you in superfields, what will happen is that my theory would be the following. So this will be C d phi plus phi square plus C phi, and again, I'm assuming that you can figure out how I write a Lie algebra. So this is a pairing, sorry, CC phi, yeah, sorry. C phi, yeah, thank you. Right, so this is my theory. It is twisted and equal to, but it's more complicated. So the statement is the following, that, so I can tell you the statement, but it's written, I think, explicitly in our previous paper. So the statement is the following, that if you take this theory and choose some Lagrangian, so you take the theory on S on L, then you can identify all these fields to this cohomological Donaldson-Witten theory, which is a twisted n equal to Young-Mills. But a priori, this theory has more fields.
Auxiliary.
Right, but I mean, I'm very afraid to say the word auxiliary. In one world, it's auxiliary. In another world, they're important. I don't know. Yeah.
Sorry, what is, I'm trying to, phi is bosonic. Is C fermionic or bosonic?
So they have degree. So this is a superfield of degree 1. This is superfield of degree 2. But if you expand them, so that's the conventions I will use. So for
I mean, on S, but back on the target, on the G1 plus G2.
well, it's a collection of forms. No. Right. So it's a collection of forms. So by abuse of language, I will use this notation C0 plus C1 plus C2 plus C3 plus C4. Okay, and then the same for these guys. Then I will have phi 0 plus phi 1 plus phi 2 plus phi 3 plus phi 4. Now, if you look at usual things, this guy is superfield of degree 1, this is degree 2. So it means that physical field of degree 0 is this one. So this is degree 0, and this is degree 0. So then, if you want to understand what physical theory is, you take this section and you restrict to degree zeros. So if you restrict to degree 0, then your theory would be this one. It will be basically phi 2, and then you will have d C1 plus phi 2 C1 C1. So plus correction. So if you integrate it, this is basically nothing as just a trace of C1, which f of C1. So this is second Chern class. So we are trying to quantize second Chern class. Yep. I'm saying is you have to work. I mean, I'm not just, I mean, supersymmetry people ask me, I said, there exists this identification. Then you have to sit down and discuss all these issues. I'm not talking about these issues. No, it's, so these guys is combined. So, I mean, the conventions are very strange, but this is phi 2, this is field strength. Maybe there will be 1/2, whatever, like this. Oh, sorry, I forgot to write this term phi 2 square. Sorry. Yeah, thank you. So this is basically a BV sort of version. That's why we call it Donaldson-Witten theory. Okay, good. So let's, massage the theory more because it contains actually a lot of algebraic structure already. So what you can observe formally is the following thing, that instead of writing this space of maps, you can write the following thing. So you can introduce, so here when you have superfields, right, you have, this is what here will have x and thetas. Then I can introduce for you another variable xi of degree -1. Okay. So what I can now, instead of talking about these guys, I will talk about T1 of sigma 4 plus R of degree -1 to G of degree of 1. Now my superfields now, you can actually, by looking at this, figure out very easily that my superfield A is now defined as a C plus xi of phi. So degree 1, degree 2, degree -1, degree 1. And if you basically work with this guy, then this section can be written as follows. So this section will be the following. It will be A, D plus D xi, A plus A cube. So this is formally Chern-Simons theory, but with this funny superfields theory. So let me allocate one board to discuss the thing. Because when you write in superfields, it's not a simple rewriting because there are much more information. So let's just think about what we are doing. So I have this diagram, which I want to keep. So I have 0 forms, I have differential 1 forms, I have 2 forms, I have 3 forms, I have 4 forms. So this is my superfield C sitting here. Then I'm having here 0 forms, so everywhere here's DRAM, DRAM, DRAM. And then I have here 1 forms, DRAM, 2 forms, 3 forms, 4 forms. Then this operation, so this was to me phi, or if I put them together, this will be with psi. So this operation acts like this. So this is identity map. So this is identity. Or in superfields, this is just basically this psi derivative. Now, all this stuff comes with the ring structure because I will multiply my superfields according to this guy. It means that if I take any 2 guys from line here and multiply on each other, they are 0. If I multiply guy on this guy, I end up in a line here. So this comes with the ring structure already. So this is a DGA. Okay? Sorry, you didn't get. So I write to you spaces, right? And I wrote to you differential. But I have to write to you ring structure, right? So you know how forms, differential forms are multiplied if I would have only this line, right? Now I added another line. I have to give you a rule what will happen if I multiply this form on this form. Okay, I'm telling you when I wrote a superfield, if I multiply anything psi phi 1 times psi phi 2, this will be 0, right? So I'm telling you that if I write these guys, and remember the superfield, this comes with a fixed ring structure. So any multiplication of this line is 0, multiplying this line on this line brings me down, etc. Okay? Yep. Good. So let's keep this picture, and then let me write then also more familiar to physicists. So if I will expand, if I use these things with the phi's over there, then I will have my BV structure in the written in the forms would be as following. I will have delta C0, delta phi 4 plus delta C1, delta phi 3 plus delta C2, delta phi 2 plus delta C3, delta phi 1 plus delta C4, delta phi 0. Okay, so now this is where all this BV push forward story comes. If you stare at this structure, and remember that in degree 0 I wrote to you this section. So what is very tempting, if I introduce actually self-duality conditions, right? So I will split. So if I introduce that my C2 fields can be decomposed as a C2 plus C2 minus. So I introduce symmetric, and I write phi 2 is equal phi 2 plus phi 2 minus. Then this guy, I basically will split in 2 parts, right? So what I will do, I will write to do C plus delta phi 2 plus delta C2 minus, which delta phi 2 minus plus, okay? So then what's very tempting is the following, that you could call this space, this would be what I call M infrared, and then these guys I will call M ultraviolet. So I can ask, can I integrate those fields in a consistent way? So please observe with the following trivial statement that if I just look at the action at degree 0 and restrict to these things, what will I have? So if I take this action and restrict to degree 0, I will have phi 2 plus then I will have f of c1 plus f2 plus square. So if I integrate these guys, this is just basically will be f of c1 wh star f of c1 plus topological term. So this is actually Young-Mills. Yeah, I use Euclidean metric, I mean, or you use Minkowski metric if you allow to complexification of the forms. Because star product squares to 1 on Euclidean metric and squares to -1 on Minkowski metric. So if you want to do this in Minkowski, you have to complexify everything. But you can do it in principle, okay? Okay, good. So that's what you are doing, and what we would like to basically understand the structures, what's going on, etc. So there are some. So idea is the following: that can we do here BV push forward, forward map. And of course, it's in all generality, it's very complicated, etc. And in abelian case, I will tell you the result. But before we go in there, let me discuss some things. So statement number 1. So of course, I wrote to you this BV action, which I can write like this. I expand in components, etc. So if I take my action like this and restrict to M infrared, so it's restriction. So it means that I put all these fields to 0. So first of all, one obvious statement, it does not have to satisfy master equation, because if you take a solution of master equation, you restrict it, it does not have to satisfy. But if you write this guy, actually, this does satisfy master equation on M infrared. Okay, so it just happened. There are some sort of technical reasons, so it's an accident, but it does. Second, of course, as I told you, if you restrict guys to degree 0, you can see that you get Young-Mills. So in principle, the claim is that this is a BV formulation. I mean, do it to Castello. Sorry? Yeah, destroyed. Yeah, absolutely. It does not destroy I mean, I just do pure restriction and it does not destroy, but it's not automatic. You have to check, because in principle, this does not work. Okay. Yeah, it's just purely restriction. Push forward is very complicated. Push forward a priori, if you do push forward properly in non-abelian things, it will involve infinity many diagrams. So this is, doesn't, I mean. No, I have to, if I do push forward, honestly, I have to find a Lagrangian where I do proper integrations. I will have, Gaussian integrals, I will have diagrams, so there will be infinity many terms if I do it honestly. I'm not integrating out anything. I'm just telling you that if I just restrict the things, I'm trying to convince you of the following fact. I'm saying that if I take a BV action, I restrict on this space. From one side, you can check it satisfy master equation. From another side, if I look at degree 0, it's just Young-Mills theory. So this is BV formulation of Young-Mills theory. Nothing like anything else, okay? Good. Yep.
Does the integral, maybe we should stop asking you about the map where we integrate out MUV, but does that integral converge in any way?
Well, what it can converge in the following way. So honestly, what I have to do, and this can be done. So you have to choose Lagrangian here and integrate. Now, if I choose Lagrangian here, for example, the very good way of choosing Lagrangian, I will use Hodge theory, okay? And then basically what I'm saying that in abelian thing, it will be just Gaussian integration, okay? So modulo 0 mods, modulo cohomology, you can say that in abelian case, this is almost result of BV push forward. For non-abelian case, it will generate infinity many things, okay? So, but what's important that BV push forward, it's a thing when, in a way, you integrate some fields in BV consistent way. So I will tell you that I will write a non-local Young-Mills theory with infinity many terms, which should be topological in some sense. I mean, there is this sort of folk story that these two theories are quasi-isomorphic in some sense, okay? So far, so good. So let me make one last comment about the thing. So let me take a color chalk. And so actually, if you change Lie algebra here, so if you change this dj there, so what we are doing when we go into this infrared space is the following things what we are doing. So you can observe that if you take this dga and restrict, so what I have to do, I have to first split these guys, 2 minus, and then I split here omega 2 minus plus omega 2 plus. Then you can observe the following fact that this guys is, so this is a dga subalgebra. Okay, and then moreover, this guy is dga ideal. So it's dga ideal. So if I call this guy A0, this I call I. So then basically Castello algebra is just equal to A0 quotient by this ideal. So if you take this as your DGA, then you steal this form as true. So Young-Mills is actually, well, again, it's not our result, it's old result. Yeah. Is it, oh, well, it depends on the language. Of course, if I mean, this is what I'm exactly doing. I'm just splitting to BV manifolds. But here I'm discussing something else. I'm discussing this space. So it's, I mean, there is no symplectic structure here. Basically, what I'm telling you that in full theory, you can do superfields, which is freely generated. If you allow me to invent crazy superfields to which supersymmetry people are not used, so I have a superfield with a lot of tables of relations. When I multiply, I get there, etc. So formally, it's still DG8 respect all things, and then, you know, that's what I'm saying. But again, supersymmetry people not used to this, they like freely generated. But if you allow superfields with a multiplication table, not freely generated, then this statement is still true. So Young-Mills satisfy the thing. Okay. So let me I have to tell you something about the equivariant stuff. But what you can do here before introducing equivariance, what you can do, you can actually take and try to do push forward, and for abelian case, you can carry hold this program and you get basically this type of complex where these lines get, replaced by cohomologies, and then you get some basically complex like this, and this would be result of, you will get BV action for abelian Young-Mills with some cohomologies which depends on zero modes. But basically it's the same thing. So roughly speaking, you can say that the abelian case is the same. In non-abelian, you generate infinity many diagrams. Okay, now let me, how much time I have, like 10 minutes, 5? 10 minutes, okay. So let me tell you, because so far I didn't tell you much new, it's sort of a lot of funny observations, but let me discuss what we call equivariant BV. So anyone who likes supersymmetry and who does localization, so this is a fact was observed long ago. So from one side, all this BV story grew up from gauge fixing. So you gauge fix things, you get ghost, anti-ghost, etc., etc. So this is one world. Then for people like, I don't know, Alessandro, they live in supersymmetry, they look at algebra, which squares to translation, etc. When you have to do a localization, and then, for example, you look at pest on paper, he has to mix these two walls. Supersymmetry should act on BRST, and BRST mixes supersymmetry. So you basically have to have something when BRST contains supersymmetry and sort of supersymmetry contains BRST. And that's our thing. This is what we were trying to basically invent, reproduce simple models. We wanted basically to understand how to get formulas like Peston is using in his localization within BV framework. And basically our idea was very, very, well, nice or silly that we had to modify BV framework. And there is one observation, basic observation. So we all preoccupied on this master equation, right? This should be equal to 0. Imagine it's non-zero. Imagine it's equal to some operator. And the observation is very, very basic. Then in principle, all BV stuff you can keep if you restrict yourself. So if we restrict to sort of on Lagrangian, so we restrict ourselves to Lagrangians when t vanish on them. So we take Lagrangians and we say that t is vanishing them. So basically, effectively, we would say that on Lagrangians, so now gauge fixing this operator vanishing. Then you can talk, there are some technical details, but this is roughly idea. Then you can talk about usual things about BV, that they will, if you vary your Lagrangian homology class of this sort of T invariant, or we call them T Lagrangian, then nothing will change. So all usual BV story preserved. And then you can, on the top of this, you can do BV equivariant, BV push forward. So this is a basic idea. So if master equation fails, but you require to consider class of Lagrangian when this failure is 0, then everything works, okay? So let me keep this board. Let me tell you, for example, what we want. So here, in a way, the only modifications we want to do is the following. So as I told you, we had this BV guy, for example, in these notations. So we won't basically take a Cartan model of equivariant homology. So we would add some formal guy C I V A phi plus the rest we keep the same. Okay. So what we did, we introduced this guy. So I choose some vector fields on a manifold, and if I check my master equation, what I will get something which will generate UA, a Lie derivative. So this will act as follows. It's basically C L V A phi. So this is my failure to satisfy master equation. So whenever I will restrict myself to the manifolds where they invariant. So for example, classical manifolds you restrict, you use Hodge theory, you decompose forms according to Hodge decomposition, etc. Now, to make them invariant under this, it means that my Hodge decomposition should respect this thing. So this should come from the group action, because then I can have invariant metric, etc., etc. So in this setup, everything will work. Yeah.
Is there a clear, in the first picture that you said, like more geometric, where you integrate on the space and so on, is T what it means?
T, this is T, right? So for example, you see in supersymmetry, so in BV, you like everything squared to 0. Supersymmetry does not like everything squared to 0. So what we are saying something trivial. Let's allow not to square to 0, but then the gauge fixing as such that this is 0, okay? So basically, everything will work if you restrict to manifolds invariant. And whenever people work with supersymmetry, this is exactly what you are doing. That's why the name of killing spinors, killing vectors, in supersymmetry, there is nothing. So we are saying that in this setup, we have to work with actions which respect the metric, okay? Okay, so let me just try to explain the main result of our paper. So as you can see that, you know, the only thing we are doing, we don't modify BV structure, so this story is remain true. We modify by this term, which is of course modification of the action. And then you can ask, so you can do BV push forward as well, right? So you can do equivariant version of BV push forward. So there exists equivariant version of BV push forward. Okay. So basically what you of course assume that this operator, and this is very obvious, so I raised symplexic structure, but this operator is diagonal on, so this operator is diagonal on M infrared and M ultraviolet. So it means that my T can be also split to T UV plus T infrared. So for example, if I will look at this sigma infrared, I integrate over L UV sigma, and this satisfies this now equation. For example, I can write T sigma. Then by hitting and assuming that it's satisfied, what you can find is that T infrared of sigma infrared will be equal to T infrared sigma infrared. So it satisfies the same sort of breaking of the equation. Now what's important, when you will do a BV push forward, nothing will happen with this operator. So if I do my BV push forward, my action will be modified quite drastically, because when I integrate, I will introduce green functions, propagators, etc., I will invert. But whatever I get, and if you do it correctly, so let me try to.
The T ultraviolet doesn't contribute to the S infrared, only to the T infrared. Is that right?
Sorry, say it again.
The T ultraviolet won't
Contribute. Right, exactly. Exactly, yeah, okay. So what I'm saying is that if I will calculate this effective action in appropriate framework, so I'm integrating parts, so I'm taking abelian theory, I take Donaldson-Witten where everything is simple, and I try to push to Young-Mills. What's important thing that here I still will have a very simple operator which realize LV, okay? So when you calculate the thing, so it's a concrete calculation which is written in our paper. What you get actually D equivariant, which just looks like a DRAM plus D of -1 plus U squared D minus 2. This guy squares, equivariant squares to Lie derivative, okay? It's, sorry, D minus 3. So I want, so this guy in degree 1, so this would be in usual things like contraction, but it's more complicated. So total degree 1, and then there will be new piece when this operation shift degree by -3, and this is degree 4, so this is whole degree 1. So there will be this piece. So in usual Cartan calculus, remember that usual dV is equal D plus IV. And then you typically put here U, okay? So now what I'm saying that if you perform calculations, you get these operations, everything works, you get new term, and moreover, this is not a derivation. So this is what mathematicians will not dream to get it, because this is basically perversion, because we invent non-local version of Cartan calculus with homotopy operators, etc., etc. So I think I have to finish. So let me just say, so this is basically the moral of our paper. This is this calculation with concrete formulas. So basically if you draw these diagrams for Castello complex, we give you all these operations, which is very complicated. And of course, physics tell you that everything works, but it took us longest time actually to check these identities by hand and using, Laplace, etc., because you don't believe physics before you check the things. But amazing thing that you get this stuff, so you get basically a Cartan calculus non-locally realized, not, so we did this calculation properly on abelian theory only. It's not a derivation. That's why you cannot extend it, for example, for non-abelian Young-Mills, because if it's not a derivation, it's not that easy. And no. So it has, part of the thing, it has these operators. So it has this type of operators, D-dagger. So what physicists will write as a D-dagger Laplacian. So this is full of these operators, which is non-local. Okay, and so physically, I don't know what it is. So mathematically, it's a very curious result. Physically, maybe one can say there exists some part of observables which has this non-local thing, but it's basically a supersymmetry in a local disguise. And of course, I'm not sure that what we can say anything, clearly about physics. It's more like a very curious formal result, and it's actually very powerful, example of using BV push-forward map when you get mathematically non-trivial result, which you will not dream of. And of course, going to non-abelian case, it requires of counting a lot of diagrams. We try to think a bit about this, but we don't know how to organize theory, etc. But there can be maybe some corrections and stuff like this. Okay, thank you. I will stop here.
So, are there questions?
So, if I'm not mistaken, the splitting is, most of the splitting at least, only depends on the conformal structure, not on
Correct.
and therefore we could try performing, I'm assuming that your actual choice of vertical Lagrangians, the other ones, depends on the metric.
Right, but to integrate over fiber, I actually have to introduce metric, which is invariant metric, so it's much stricter.
Yeah, so here's my question. As I perform a conformal transformation of that metric, keeping the conformal, it might be interesting to study the thing in parentheses.
Yeah, that's a good point. No, absolutely, yeah. I think it's an interesting point. You see, in this story, what's actually confusing to us, because you're taking topological field theory, you do partial integrations, and then sort of the core terms are non-topological. So it's hiding in determinants, etc. So it's this interplay between topological and non-topological, yeah. That's a good point. But in a way, secretly, nothing should depend on the metric, because if you do calculation in a big theory, and you just integrate fiber-wise, right? So in a way, all structures, should not depend on the metric. That's what I would anticipate physically.
So about that, would it be that if you take an observable which is not correct in the sense of the topological theory, you would still get the expectation value of the Young-Mills, for example?
Right, but you see here, so there is this formal belief is that this anti-PV push forward two theories are quasi-isomorphic, which is to normal people sounds sort of crazy, but what is going on that if I take a observable in one theory, it becomes highly crazy non-local in another theory and vice versa. Of course, keeping track of this, it's very, very complicated. But if you look in finite dimensional, you can prove that two theories are quasi-isomorphic. So BV gives you quasi-isomorphism, basically. But of course, I'm not saying that Young-Mills and Donaldson-Witten theory are the same. That's a crime. But I'm saying there is a very, very non-trivial map. So for example, from this nonsense, you can think that exists Young-Mills theory, and if you go to Donaldson-Witten theory, you can add a lot of non-local terms, and this should be quasi-isomorphic to Young-Mills theory. But of course, it's just general blah, blah. You cannot control this process very clearly.
Could you say a bit more about how the supersymmetry is related to the BV in the last one in particular? If you look at, say, the Maxim theory, there's a standard BV quantization where you look at the BV quantization and equals to Young-Mills.
Right.
And then in what you're doing, you're using a different picture with on the phase bit looking like a rather different dose structure.
Right.
And
Right. So the whole idea exactly, so BV, you know, if you do gauge fixing, you go to burst T, then, you know, everything squares to 0. So for example, if I go to, you know, so for example, typical thing, if you go to, so you write delta A, it's a connection. I will use now physics notation. So psi goes to psi. Delta psi goes to, I think dA, I think physicists call this field phi. Okay, so this would be typically notations. If you mix supersymmetry, so this is twisted supersymmetry and these things, and then you will typically put some ghost dAc plus C psi, okay? So if you look at this transformation, they will square to 0. Okay, they will square to 0. So now what we want to modify the thing. So what we are adding, we are saying that this will come from gauge fixing. So here you will add terms like I, V, F, and then once you put these terms, your guys will square to LV. So you want to have consistently what you have on physical fields and on burst T, because if you look at all the papers, what Peston did, he by hand just postulated supersymmetry on, you know, this ghost, anti-ghost sector, Lagrange multiply. A priori, you don't know how to do it, but you cannot use localization because you have supersymmetric Young-Mills, then you do gauge fixing, and a priori, right? I mean, these guys square to some particular translations, but these guys do not square. But you want to have a mixture of supersymmetry with action on this ghost sector, and you would like this is all consistent. So at least in particular restricted framework, we are telling you know how to do it. So if we use this equivariant type of AKZ construction and do gauge fixing, then we can work out. And basically, this was our previous paper when we we wanted to reproduce these formulas, which people like Nekrasov, Peston wrote for a long time, but we wanted to get from gauge fixing of BV formalism. This equivariant BV formalism, that was our original goal. But it's again, it's a mixture of two worlds, which is a priori, even in terms of humans, I mean, do not intersect very much. I mean, I think people do supersymmetry on BV, and they don't talk to each other very much. Yeah. Well, I mean, no, this psi, it's basically one of the components of this phi, etc. So if you look at papers from 80s, they call them ghosts, etc. So if you look at paper by Bolet, Zinger, they call this ghost and they call this ghost. I mean, I will just drop all these funny names and this is fields and you expand them in degree, etc. And stop using this, you know, silly names. I mean, that's my. Right. Right, but absolutely, but then you have to go to the theory and try to connect two languages. I mean, the connection is not canonical, but you have to think how to do it. Yeah, I don't know. It's a problem how to connect two worlds, and I'm not saying there is a unique solution for this problem. I mean, it's a model-dependent stuff, etc. But all this stuff, whatever which people write in supersymmetry for twisted things for whatever 20, 30 years, you can get just this particular BV fixing with all fields just, you know, rolling down and then nothing else.